If math has been driving you crazy, or if you're finally admitting you're lazy, and your test grades have been dropping, it's time to get your arrows popping. Ladies and gentlemen, welcome to another video from Fort Bend Tutoring. This is Mr. Witt, and today we have a video for you on graphing the secant function. That is right. And so before we begin, go ahead and click on that subscribe button. Go ahead and click on the bell icon so that you can be notified when we are uploading new and fresh content for you. Oh, yes. Go ahead and do that. And now what we're going to do, we're going to take a gander. We're going to take a look at the 4 problems that I have prepared for you today for today's tutorial. That's right. 1, 2, 3, 4. Go ahead and take that in. Yeah. Nice. They look good, huh? There you go. Yeah, we'll be doing those together. Yeah, you and I. So after your appetite has been properly whetted, let's continue with secant. That's right. And so f of x equals to secant x of 1 divided by cosine of x. Secant is a reciprocal function. It is, because it's the reciprocal of cosine. That's right. 1 divided by the cosine of x is secant x. Good to know. The domain of secant is x is such that x cannot equal to the product of 2n plus 1 times pi divided by 2, where n is any integer. The range is from negative infinity to negative 1 union 1 to infinity, including negative 1 and 1. The graph of secant is symmetric with the y-axis. So that means that the function is an even function. In other words, secant of negative x is equivalent to secant of x. These are things that are good to know. Good to know. So take that in, continuing on. We have a reminder of the cosine function. Now remember, secant is the reciprocal of cosine. So it's good to know that when graphing cosine, because that's what we're going to use to help us graph secant, thank you, that cosine is the reciprocal of secant and vice versa to help us graph our secant functions here. So with our expanded form of y equals to a times cosine of bx minus c plus d, we'll be using this form in order to help us graph our secant function. So as a reminder, check out how we go about finding the amplitude, the period, the phase shift, the vertical shift, and most importantly to me, the increments. Oh, how the increments are important to the process. Oh, yes, they are. So for problem number 1, we have f of x equals to secant x. And the first step when graphing your secant function is to convert this into a cosine function. That's right. We're just going to be swapping out, temporarily that is, the secant function with a cosine function because the reciprocal of cosine is secant. So since I'm going to be way more familiar with cosine than I am secant, I'm actually using cosine as a tool in order to graph the secant function. So my first step was to swap out the secant function with the cosine function. All right, so now that we have translated this into a cosine function, what we'll do now is we'll identify the different attributes of this cosine function so that we can graph it. First of all, the amplitude is the absolute value of our a value. In this case, our a value is 1. So that means that the amplitude is 1 of the cosine function. Then our period for this cosine function is going to be 2 pi divided by our b value. And our b value is 1 because we have 1x. The coefficient on the variable of x is going to be your b value. So of course we can simplify this. So that means that your period here is going to be 2 pi. So your phase shift is going to be the quotient of c and b. So our c value in our equation is 0 and our b value is 1. So we'll have 0 over 1, which equals to 0. Your vertical shift is 0. So your d value is 0. So we'll pay attention to that. And then finally, you'll have your increments, which is the period divided by 4. Our period is 2 pi divided by 4, which simplifies to give you a result of pi over 2. And these are the initial values that we'll use in order to construct our secant function. So let's go ahead and red box it. That's right. So the amplitude is 1 for the cosine function. The period is 2 pi. Our phase shift is 0. And our vertical shift is 0, as well as the increments being pi over 2. So now you'll be starting your XY chart, the points that you'll use to graph your cosine and eventually your secant function with your phase shift. Always start with the phase shift. And since our phase shift is 0, we're starting at 0. So I have a value of 0, and we keep adding our increments to this initial value. So 0 plus pi over 2 is pi over 2. So we got a value of pi over 2 right there. Thank you. And then we add pi over 2 plus pi over 2. That gives you pi. Then adding pi over 2 to pi, you end up with 3 pi over 2. Like so. And then finally, 3 pi over 2 plus pi over 2 gives you 2 pi. So these are going to be the 5 values of x that we'll be plugging into this cosine function to help us graph the secant function. Well, plugging in 0 into our value of x into the original equation here, cosine of 0 is 1. So we have a value of 1 there. Cosine at pi over 2 is 0. Then cosine at pi is -1. Cosine at 3 pi over 2 is 0. And cosine at pi over 2 is 1. Yeah, so we have 5 points that will help us graph the cosine function, which in turn will help us graph the secant function. So starting out graphing our function here, we'll have 0, 1 as a point. We'll then have pi over 2, 0, which is going to give me a point here. Then at pi, I'm at -1. Then I'm going to be at 3 pi over 2, which is at 0. And then finally, we have a point at 2 pi and 1, which gives me a point right here. Well, graphing the cosine function, I'm going to use dashed lines to graph this. Just like so. All right. So I have my cosine function graphed with dashed lines because we're here to graph the secant function, not the cosine function. Then the next thing we're going to do is we're going to recognize that since secant is the reciprocal of cosine, everywhere our y value is 0, we're going to end up with an asymptote. Because placing 1 over 0 when we find the reciprocal for secant, that result will be undefined. So you can't divide by 0. So because of that, it creates an asymptote for our secant function. So what I'll do is I'll show that at pi over 2, I have an asymptote. And also at 3 pi over 2, I also have another asymptote. Just like this. And also keep in mind, this is going to be the result for 1 period of secant. We could go ahead and expand this by continuing the same points to the left of our graph, just as we did with the right. So you'll end up, for instance, at -pi over 2, you'll be back at 0. And then at -pi, you'll be at -1. And then at -3 pi over 2, you'll be back at 0. So this can continue this way. And once again, everywhere we are touching the x-axis will be an asymptote. So you'll have an asymptote here, and you'll have an asymptote here. And this is obviously helpful when the directions ask us to graph more than 1 period of a function. Just note that my initial graph here was for 1 period of secant. So that being the case, let me show you what your graph of secant will look like. Everywhere you have a peak and a valley, you're going to be drawing a parabola that has a common point with the peak or valley between the two vertical asymptotes. So that means that I'll have a parabola set up here. I'll also have a parabola set up here. And it just continues in this fashion into infinity. Oh yeah, just like that. Okay, so in blue, I've displayed the graph of secant. Just like that. And this, ladies and gentlemen, is the graph of your secant function. Done and done using our graph of cosine as a tool. That's problem number 1. Let's move along. In number 2, we have y equals -secant of pi over 4x minus 1. So in a problem like this, we're going to have several transformations. For instance, I know because this value is negative in front that we have a reflection across the x-axis. I also know that we're going to have a horizontal stretch because of our b value of pi over 4. And I also know that we're going to have a vertical shift of -1. All right, that's if you're keeping up with your transformations. However, the technique that I'm showing you today, your graph doesn't rely on the transformations as we are finding out the actual points from the function. So remember that your first step is to rewrite the initial function as a cosine function. So you'll have y equals to the opposite of cosine of the quantity pi over 4 times x minus 1. And it's this cosine function that we're going to use in order to graph our secant function. All right. So here we have it. So now that we're going to focus on the cosine function, I know that the absolute value of our a value is +1. I also know that our period is going to be the quotient of 2 pi and our b value, which happens to be pi over 4. So by multiplying 2 pi times the reciprocal of pi over 4, which is 4 over pi, we're going to end up with 8 as our result here. That's right. So your period for this problem is 8. Your phase shift is going to be the quotient of c divided by b. So your c value is 0 divided by your b value, which is pi over 4. And 0 divided by any other number is 0. Your phase shift in this case is -1, which means that the entire function will be moved down 1 vertically. And then your increments are going to be your period divided by 4. So our increments are going to be 8 divided by 4, which is 2. So my increment value is 2. So we'll always start at our phase shift of 0. So I have 0 here, and then we'll keep adding 2. So you'll have 2, 4, 6, and 8. 0, 2, 4, 6, and 8 are going to be the values that we plug into our cosine function. And since we'll be using 0, 2, 4, 6, and 8, I probably want to change up these ticks here, all right? Because these are not going to be ideal for this particular problem. So being aware of the x values, I'm able to change our ticks on our Cartesian plane here. So that's looking a lot better. Now plugging in our values of x's into the cosine function to get our y values, plugging in 0, pi divided by 4 times 0 is 0. Cosine at 0 is 1, and the opposite of 1 is -1. So -1 minus 1 gives me a result of -2. Then plugging in our x value of 2, you'll have pi over 4 times 2, which reduces to pi over 2. Cosine at pi over 2 is 0. The opposite of 0 is 0. And then 0 minus 1 is -1. Then plugging in the number 4, you'll have pi over 4 times 4, which is 4 pi over 4, which simplifies to give you a value of pi. Cosine at pi is -1. And the opposite of -1 is +1. 1 minus 1 gives you a result of 0. Like so. Plugging in the number 6, you'll have pi over 4 times 6. That's 6 pi divided by 4, which reduces to 3 pi over 2. Cosine at 3 pi over 2 is 0. The opposite of 0 is 0. And 0 minus 1 gives you -1. Finally, plugging in the number 8, you'll have pi over 4 times 8, which is 8 pi over 4, which simplifies to give you 2 pi. Cosine at 2 pi is 1, and the opposite of 1 is -1. -1 minus 1 gives you a result of -2. So these will be the 5 points that we use to graph our function. Remember that every value of x where we were able to generate a value of 0 for the cosine will end up giving us an undefined result when it comes to our secant function. And when did this occur? This occurred when x was 2, and this occurred also when x was 6. These are the values where we ended up with the result of cosine being 0. Because the reciprocal of this is undefined, that's why you want to make sure that this is where you're going to have a vertical asymptote. So knowing that, I know that at 2, I'm going to have a vertical asymptote. I also know that at 6, I'm going to also have a vertical asymptote. And then we'll go ahead and plot our 5 points. So we definitely wanted to keep up with where these vertical asymptotes occur. It's not necessarily easy to see from your XY chart where those vertical asymptotes occur because we had this vertical shift of -1. So that's why you want to go ahead and make note of that before you start graphing. So we'll begin with the point 0, -2. Gives me a point here. Also, we have a point at 2, -1. Then I have a point at 4, 0. Then another point at 6, -1. And we also have a point at 8, -2. All right. And remember, this is going to be our graph of cosine that we're going to use to help us graph our secant function. Recall that everywhere you have a peak and a valley is where you're going to end up with a parabola to show your secant function. So that means that I'm going to have a parabola here, like so. All right. And remember, if I wanted to continue this to the left to show more than one period, I can show that at -2, I would have a point at -1. At -4, I'll have a y value of 0. And at -6, I'll be having a point at -1 again. So we can go ahead and continue this cosine function, which in turn helps us graph more of our secant function on this particular graph. So let's go ahead and get our vertical asymptotes in play as well. And notice that we have a vertical asymptote at every 4 ticks. 1, 2, 3, 4 is the separation between all of our vertical asymptotes. So 1, 2, 3, 4 to the left will give us a vertical asymptote at -2. 1, 2, 3, 4 gives us another vertical asymptote at -6. So this helps you see more of the peaks and valleys in our cosine function that we'll use to create our secant function. So here I have my parabolas set up right there, okay, and then I got a parabola set up right over here, okay, just like that. And over here, okay, you get some too. There you go. You get half one. You get half one. Okay, because you're not fully grown yet. So there you go. This is our secant function with all of our transformations in play. Remember that I said that we would have a reflection across our x-axis, that we would also have a horizontal stretch, and that we would also have a vertical shift down one, and you would end up with the following secant function from those transformations, utilizing cosine as a tool to help us graph it. And that was problem number 2. Continuing on. Guys, just wanted to remind you that you can always set up a paid online tutorial today with Fort Bend Tutoring and myself. So if you like my tutoring style, you can very well get your own one-on-one private tutoring session with me, Mr. Witt, by going to tutormemath.net. All right, go check out our website, and we have many services that may help you on your academic journey. And let's continue on with problem number 3. In problem number 3, we have f of x equals secant of the quantity x minus pi over 3 plus 2. So our first step is going to be to rewrite this as a cosine function, knowing that we're going to use cosine as a tool to help us graph the secant function. So now that we have it rewritten, let's go ahead and continue, knowing that the amplitude of our function is 1 because the coefficient on our a value is 1. And then our period is going to be 2 pi divided by b. Our b value in this case is 1, so the period is 2 pi. And then our phase shift is c over b. So in this case, we do have a c value. And recall from your expanded form, the opposite value that's within the parentheses is the c value. So instead of using negative pi over 3, our c value is going to be positive pi over 3. And that's going to be divided by our b value to end up with a phase shift of pi over 3. This is going to be where we start graphing our function. So let's once again make an adjustment to our ticks down here. When it comes to our d value is going to be 2, so we have a vertical shift of 2, and our increments are going to be the period divided by 4. So our period is 2 pi divided by 4, so we end up with pi over 2. Red box it. You're going to end up with your amplitude for your cosine function being 1. Our period is 2 pi. Our phase shift is pi over 3. Our vertical shift is 2, and we have our increments, which are pi over 2. So that means as far as our XY chart is concerned, that we start at pi over 3. You always start at the phase shift, and then you'll keep adding pi over 2. Now, we do know that pi over 3 is equivalent to 2 pi over 6, right? Okay, and we also know that pi over 2 is equivalent to 3 pi over 6. I wanted to get a reference of a common denominator for us to use so that it'll be easier to add our increments. So since I have rewritten pi over 3 with an equivalent fraction of 2 pi over 6, and I've rewritten pi over 2 with equivalent fraction of 3 pi over 6, we'll be using the 3 pi over 6 from this point on to generate all of our remaining x values. So adding 3 pi over 6 to 2 pi over 6, this gives you 5 pi over 6. So this value cannot be simplified any further, so this is going to be the x value that we'll use next. Then adding 3 pi over 6 to 5 pi over 6, you get 8 pi over 6. Well, this simplifies to give you 4 pi over 3. Okay. Then adding 3 pi over 6 to 8 pi over 6, this is going to give you a result of 11 pi over 6. And one more, adding 3 pi over 6 to 11 pi over 6, which is 14 pi over 6. This simplifies to give you 7 pi over 3. And now we have all of our x values that we need to graph our cosine function. From here, we'll keep in mind that this is also the quantity of x minus 2 pi over 6. Okay, and then depending on our denominator, we'll be able to use either of these versions of the value for cosine to generate our y values. And you'll see what I mean in a second. For instance, let's start off by plugging in pi over 3. Well, plugging in pi over 3 minus pi over 3 is 0, and cosine at 0 is 1. 1 plus 2 gives you a y value of 3. Then we'll be plugging in 5 power over 6. And since it has a denominator of 6, I'll be using this version right here. So 5 power over 6 minus 2 power over 6 gives me 3 power over 6, which is power over 2. Well, cosine at pi over 2 is 0. Now remember that since secant is the reciprocal of cosine, once we generate a value of 0 after using the cosine function, we should know that this is where an asymptote will occur. So you'll have a vertical asymptote at this point. So continuing on, our actual point though is going to be 0 plus 2, which is 2. Then plugging in 4 pi over 3, 4 pi over 3 minus pi over 3 gives you 3 pi over 3, which is pi. Cosine at pi is negative 1. Negative 1 plus 2 is positive 1. So we'll end up with 1 as our y value here. Then plugging in 11 pi over 6 for our x value. Let's use this version. 11 pi over 6 minus 2 pi over 6 is going to give you 9 pi over 6, which is 3 pi over 2 when you simplify it. Cosine at 3 pi over 2 is 0, which means that this is going to be another location of a vertical asymptote. So continuing on, that will be 0 using cosine, and 0 plus 2 is 2. Finally, plugging in 7 pi over 3. 7 pi over 3 minus pi over 3 gives you 6 pi over 3, which reduces to 2 pi. Cosine at 2 pi is 1. And then 1 plus 2 is 3. All right. Also, you can see that it actually creates a little pattern here. 3, 2, 1, 2, 3. Just saying. Graphing our first point at pi over 3, 3. I have a point right here. Then my next point is 5 over 6, 2. Right here. Then I have a point at 4 pi over 3, 1. I also have a point at 11 pi over 6, 2. And then I also have a point at 7 pi over 3, 3. Okay. Our vertical asymptotes are occurring at 5 over 6. So we have one there. And we also have a vertical asymptote at 11 pi over 6. All right. And of course, this is going to be for one period of secant. So then, doing our dashed line here for our cosine function, and then recognizing that we're going to have parabolas that are going to be opposite of what we have going on here, we'll end up with the following secant function. So we'll have this going on like that, and then you'll get a little half right there, and you'll also get a little half right there. Okay, and there you go. That is going to be your secant function. All right. And I think we can do it a little better, right? And we know the pattern is going to go from 3 to 2 to 1, then back up to 2. All right. And we also know everywhere we're going to be at a y value of 2, you have a vertical asymptote. All right. So different ways to keep up with this. Like so. All right. So that helps me to do the following. I can extend my cosine function, which in turn allows me to flesh out more of my secant function. There we go. All right, so is that better? You like that? We have more of our secant function shown. Yeah, a little messy in this area. Yeah, a little messy, but yeah, you should know what's going on there. Just saying. All right. That's problem number 3. Moving on. For problem number 4, we have y equals negative 1/2 secant x plus 1. Well, our first step is to rewrite this as a cosine function. This is negative 1/2 cosine of x plus 1. Yeah, we're going to be using that. Let's continue. So the absolute value of our a value is the amplitude. So here our amplitude is 1/2. Yeah. Our period is 2 pi over b. So we have 2 pi over 1, which gives you 2 pi for your period. Your phase shift, in this case, is going to be 0 over 1. So that's just 0. You have a vertical shift of 1, and our increment is going to be 2 pi over 4. Simplified gives you pi over 2. All right. So there we go. This is your problem number 4. Let's go ahead and red box it. Red boxing it. That's right. Amplitude, phase shift, vertical shift, and the increments, my favorite part. And that means that starting at the phase shift, we'll be using the following x values. We'll be using 0. We'll use pi over 2, pi, 3 pi over 2, and 2 pi. And we get these values by starting out with the phase shift and then adding our incremental value of pi over 2 each time. Then let's go ahead and plug in our value, shall we? Plugging in 0, cosine at 0 is 1. 1 times negative 1/2 is negative 1/2. And negative 1/2 plus 1, it's 1/2. It is 1/2. Plugging in pi over 2, cosine at pi over 2 is 0. 0 times negative 1/2, still 0. 0 plus 1 is 1. Yep. Now, at pi, you'll have cosine of pi is going to be negative 1. Negative 1 times negative 1/2 is positive 1/2. 1/2 plus 1 is 1/2. And you know what? I'm going to write it just like that, 1/2. Then we'll have 3 pi over 2. Cosine at 3 pi over 2 is 0. 0 times negative 1/2 is 0. And then 0 plus 1 is 1. From here, you'll have 2 pi. Cosine at 2 pi is 1. 1 times negative 1/2 is negative 1/2, and then negative 1/2 plus 1 gives you positive 1/2, and we have 5 points that we can use to graph the cosine function. All right, so at 0, we're at 1/2, right? Got a point right there. We also have a point at pi over 2, 1. Pi over 2, 1 is here, okay? And then we have a point at pi 1/2. There we go. And then you have a point at 3 pi over 2, 1. Then I have a point at 2 pi 1/2. What do we know about this? We know that everywhere we got a value of 0 from our cosine function, the secant function would be undefined. That means when we initially generated a 0, like for instance, when I took the cosine of pi over 2, this is going to be a vertical asymptote here, and I'm going to end up with a vertical asymptote at 3 pi over 2 as well. So knowing that, we can begin by showing that our vertical asymptotes occur here and here, just like so. Then using a dashed line, I can show what my cosine function would look like, knowing that I would have a vertical shrink with that 1/2 a value. That's going to create a vertical shrink, which is why it's not as tall as it normally would be, and also why our amplitude is only 1/2 instead of 1. And then what we could do is we could expand on this if we wanted to, knowing that at negative 1/2, I would end up with a point at 1. Also at negative pi, I would end up with a point at negative 1 1/2. And also keep in mind, guys, that this is a even function. So everything to the right of 0 is going to be a mirror image to the left of 0. Okay, so that's another way of recognizing how you can go ahead and span on multiple periods of your cosine, eventually your secant function. Okay, then let's go ahead and show that at negative pi over 2 is going to be a vertical asymptote, and at pi over 2 you're going to have a vertical asymptote. All right. So going ahead and graphing our secant function, we're going to be keeping in mind the peaks and the valleys. So let's start right here. We got a valley right there. We also have a valley right here. We end up with a valley here and a peak over here. All right. That's it. This is going to be our graph after we have reflected it across the x-axis. That's why it's looking different from the other ones, because it had a vertical reflection across the x-axis. Also, we had a vertical shrink, so it's not as tall as it was. This area here with the cosine function is not as steep as it would be. And then, of course, everything's been shifted up by 1 because of the vertical shift, if you're paying attention to your transformations. Once again, note that this method that I've shown you today is not using transformations. I'm only mentioning the transformations as you should be aware of them. All right. And this is going to be your graph for problem number 4. All right, ladies and gentlemen. So as a reminder, please once again subscribe to the YouTube channel Forbidden Tutoring. It has been a pleasure having this opportunity to showcase this method of graphing the secant function from trigonometry. And as always, please rate, comment, and subscribe. Peace.
Thanks for watching. We appreciate you hanging out with Forbidden Tutoring. Like the video, comment, and subscribe. Hit up our website, tutoringmath.net, and set up a private tutorial with me and FBT.